So I think, yes, it's a good time to start. Thank you for joining this advanced track. And today I'm going to talk about different best practices that you can use in developing your applications, different advanced features that Scylla has, and that you can use in your own cluster. So let's start with agenda. And as I said before, the agenda today not only covers the drivers, but also data modeling and troubleshooting using Scylla monitoring. So first of all, we are going to start with Shard-aware drivers, what advantages they provide and how they differ from non-Shard-aware drivers. Next, we'll move on to different features that the drivers have and that you should tune to have better performance and better latencies, such as using prepared statements, setting correct paging, and using retries. The next section of the presentation is going to be about data modeling and what tools you have in your toolchain to model the data in ScyllaDB and using data types such as collections, UDTs that allow you to model complex data, as well as features such as TTL, materialized views, global local secondary indexes that really add new capabilities that you can use Scylla for. And finally, when you have your cluster running, you have to monitor how it's performing. You would like to know how many queries are running on it, whether you have to scale it up, or maybe it's okay to scale it down. And using Scylla monitoring is a great way to know about the cluster, how it's performing, and if there's some problem, to pinpoint the root cause of the problem. And finally, we are going to see all those topics in practice in real time, and we'll use Scylla Cloud, real cluster running on Scylla Cloud, to see how those techniques, how those topics can be applied in real life. So let's start with Shard-aware drivers. So Shard-aware drivers are the drivers that we publish that are aware of the architecture of Scylla. And to better understand the difference, let's start with a non-Shard-aware driver. And when a non-Shard-aware driver tries to connect to Scylla, most of the non-Shard-aware drivers make a fixed number of connections to a node of Scylla. So for example, this client is making 4 connections to Scylla. However, it's not aware that Scylla has a shard architecture. So the Scylla shard architecture essentially means that each individual physical core on a Scylla node, so a physical thread on the CPU, is essentially a separate module of Scylla that avoids doing transfers between the cores that actually can be really expensive even on the hardware level, and that makes it also great to Scylla to scale with high CPU, high core count machines. However, when you use a non-Shard-aware driver, the driver doesn't know that Scylla has such an architecture, and when it establishes a connection, the connection that is established will connect to some shard, and essentially this choice will be random. The driver is not aware that the connection has been established to some shard. So as you can see, some of the shards have no connections, and for example, the shard 1, it happened by chance that it has 2 connections. And the problem appears when there's a query that has to query some data on shard 3. And what happens in that case is that the driver will send it to a wrong shard. Internally, Scylla will proxy this request to a correct shard and wait for this correct shard to send the response and send this response back to the wrong shard that the driver sent the request to, and resend this response back to the client. This can add additional latency and worsen performance. By contrast, when you use a shard-aware driver, the driver connects to each particular shard. It makes a separate connection per each shard. And when you make a query, it knows which shard to send the query to. And Scylla doesn't have to proxy the traffic between the shards, having to do this expensive operation. Next, let's move on to prepared statements and how you can use them in the drivers. So this graph is going to be presented in this presentation multiple times, and it shows a basic Scylla cluster and the way that you send a request to a Scylla cluster. And what happens in this example is that the client sends the request to a Scylla node. Automatically, this node becomes a coordinator. And in Scylla, each node can become a coordinator. It's all symmetric. And when this node becomes a coordinator, it figures out the replicas and sends the request to a correct replica. Then what this graph actually shows is a driver that sends an unprepared query. And when an unprepared query is sent, the client doesn't know that what are the replicas that the data is stored on, and it has to choose any node on random. And in most cases, this node will have to proxy the traffic to another node. So maybe to explain what prepared statements are. So prepared statements are essentially a template of a statement. So what it means is that if you have an insert statement that inserts some data into some table, a prepared statement is a template that doesn't have the actual data in the query. This actual data is replaced by markers, bind markers. And this template is stored on Scylla. It's parsed only once. And then the client can send multiple requests using this template and have much better performance since the query has been parsed. Additionally, when a query is parsed, Scylla returns some metadata about this query, and the client can now correctly figure out which node to connect to without having to connect to a non-replica node. So this is a basic example that you can use in Python driver. Those examples are very similar in other drivers.
Piotr,
Yes.
there's a few questions here. How does a specific charge within a node gets chosen?
Could you repeat the question?
How does a specific chart within a node gets chosen?
I didn't get the chart, the first portion of the question. Could you rephrase it?
How does a specific charge within a node gets chosen?
Okay, sorry, I now get it. So the way it works is that when there's a query made to some particular partition, first of all, we calculate a hash of this partition key, and this partition key hash is used to determine the replica node. And additionally, we also use this hash to determine the actual shard to send the query to. So this shard information is based on the hash and some mathematical operation. You could think of it as a modulo operation to determine the specific shard to send the query to.
Okay. How does ScyllaDB handle complex data types and queries? And what the best practice should developers follow to optimize performance in these scenarios?
So actually, in a few slides, I'm going to talk about some advanced types. So I'll keep you waiting
let's wait for that.
For that slide.
Thanks, Piotr.
So going back to prepared statements, this is how you can use prepared statements in Python. So in the first 3 lines, there's a prepared statement. And this insert doesn't have any actual data. This actual data has been replaced by question marks. So those are the bind markers in the query. And when we use session execute, we can pass the prepared statement object. And this object is very lightweight. It will be sent, as you will see in the next slide. This is a very lightweight representation of the query, and we can directly bind the parameters to those bind markers. So how it looks in the Wireshark capture, so this is the network capture, is that if you use an unprepared query, then the whole textual format of the query is sent. So as you can see, there's an update set, and the value is written in a textual format. But when we use prepared statements, we don't have to send the actual query, the textual format of the query. Instead, the driver sends a short query ID. And instead of having to serialize the data into textual format, it can serialize into a byte format. So those values that were written in textual format on the previous slide, they are now in bytes format on the next slide. So now let's move on to the final feature of the driver that I'm going to talk about, which is paging. So suppose we have a query that scans some table. So we asked Scylla to return all the data that is in particular table. When you use an unpaged query and you perform such a select, then Scylla has to do something really complex, which is gather all the data that is stored in that table. If you use the select scan of all the data in the table, it has to allocate this huge buffer of the output data. It then has to send it over the network to the client, which has to deserialize this huge buffer. And the problems with that approach is that on the Scylla side, and actually on the driver side, on your client side, you have to allocate those huge buffers, which can cause problems such as memory fragmentation problems. And the second issue is that selecting such a huge amount of data can have large latency. And this can really cause some latency problems in your cluster. However, if you use paged queries, what happens is that the Scylla cluster will not return the whole result at once, but instead it will return some fixed amount of data, some fixed amount of rows from the start, return this smaller amount of data to the client, and then the client can send the data, send the query once again, and get the next batch of data. And that way, we don't have those problems with allocating large buffers. We don't have those problems of large latencies when we wait for Scylla to gather all those potentially millions of rows. And this is a better approach, and this is quite a common mistake that can cause problems with latencies.
Piotr, there's a question from Pavel, and he's asking if there are any limits of number of prepared statements to cache.
So effectively, there are no such limits. Essentially, the cache can get as large as the memory allows the node to store the prepared statements. And I think in most cases, we successfully tested Scylla having a cache of thousands of queries. And in your typical application, I would guess that you wouldn't really have to have such a huge amount of prepared statements.
Okay, thanks for that.
So now let's move on to retries, which is a feature in the drivers. So essentially what retries are is a policy that answers a question, what to do when a request has failed on a node. So in that question, we have essentially three answers. We can retry the query, either on the same node or maybe try another node. We can immediately throw the exception, and your code has to handle it. Or maybe we can ignore the error and just assume that as if nothing bad happened. So it depends on your application which policy you would like to do. So the default policy retries at most once, and of course you can choose your own policy. And in the drivers that have different execution profiles, you can specify different policies per each execution profile. And a very important thing is that this retry policy only kicks in when a query is idempotent. So what it means is that we can safely execute the query multiple times. So an obvious example of such a idempotent query is a query that selects some data, and obviously running it multiple times won't affect the data as nothing is written, and we can safely retry multiple times. So most of the drivers that we have ship with two retry policies. So of course, there's a default retry policy, and there's also a consistency downgrading retry policy. In most of the drivers, you can very easily write your own retry policy, and in most drivers, it's very pluggable, so it's very easy to have your own policy. And of course, if there's a need, you can disable the policy. So now let's move on to a data modeling part of this presentation, and let's start with collections. So when you think of different data types that Scylla provides, such as text format, int, value, dates, decimal, double, they essentially describe only a single aspect of the data. For example, the name of a person, the age of the person, but all those types describe only a single value, the single aspect of the data. And when you have collections, you can describe groups of items in a single column. And this greatly simplifies data modeling and brings much flexibility in the way that you can design your tables. However, you should keep in mind that the collections that you have should be small, as if you have a very huge collection, for example, that could be a few megabytes large, then selecting the data from such a table will have bad latencies. So keep in mind that the collections that you keep shouldn't be very large. And if you have to store, for example, millions of elements in a collection, I think it's a point that you have to decide to use different strategy of modeling your data, maybe storing it in a separate table, not storing it into a collection column. There are two types of collections. You can generalize it that way, frozen and multi-cell collections, and we'll get to that. So let's start with some example table that has multiple columns of different collection types. So we'll cover sets, lists, and maps. So let's start with sets. I think this name is very similar, as it effectively is the same as the sets in Python, and maybe tree set in Java. And this is a data type that allows you to store some effectively some set of items. Those items are ordered by the order of data type. So, for example, in the case of text, you would expect that the data would be sorted alphabetically, and the set only allows you to have non-duplicate items and also allows for efficient removal of some element if you want to remove some element that happens to be somewhere in the set, or you want to insert some element and have it not be duplicated in the set. So here's some basic queries that you can use with sets. So in the first example, we insert a set of a single element, a single letter C, to the table. You can also append some data into the table. So the two queries at the top add element A, element B, and as you can see at the bottom, the set after all those operations consists of 3 elements. Lists are very similar. They also describe some group of elements. However, they are not ordered by the type order. They are ordered by the order that you have selected, that you have performed different operations on this list. And of course, they support duplicate elements. So this is a great example of some types of operations that you can use on lists. So the first statement just sets the list to be equal to a single element list. And then the next statements can prepend and append some new elements to the list. Next, maybe the most powerful data type, collection data type, are maps. And in other languages, in other databases, you could call them dictionaries. And they are a unique key value per set. So you have some set of keys, and each key has some particular value. So in this example, we have a map that will model some geographical position. And in the first query, we update the position. We set the latitude, longitude of this position. And we can also add a new parameter to the position. And is very flexible. The position could be described in many ways thanks to using a dictionary, a map in that example. So now let's move on to UDTs, user-defined types, and keep in mind the previous example that I have shown of modeling a geographical position. So in this example, we'll create a user-defined type, and this user-defined type will also describe a geographical position. However, this will be much more stricter than using a map because we specify upfront which fields will be stored in this type. So we specify that altitude, latitude, and longitude will be stored in geotype. And when you create a type, you can use it as if it's a normal type that is in Scylla in the create table statement. So all other tables can use it from now on. When you insert the data into a column of your own UDT, the syntax of inserting the data is very similar to the syntax of specifying a map. However, the fields are not in quote marks, and of course, you have less flexibility in specifying the names of the fields, as you have to specify them upfront. And a very interesting topic in data modeling is modeling time to live, also known as expiration time. So what TTL is a powerful feature that allows you to remove the data that is no longer needed, that has expired. And Scylla is very flexible in a way that it implements TTLs, as you can have different TTL per each column. So we would have a table that has some rows, some columns that have no TTL, that they will never expire, but maybe some single column will expire at some point of time. One way that you can specify the TTL is to set the default value of TTL on the table. So when you create a table, you can specify a default time to live parameter. This is the parameter in seconds, and it will determine after what time a row inserted to the table will expire. You can, of course, change this parameter after the table has been created. However, keep in mind that the alter table will not update any existing rows that have the old default time to live parameter. Next, if we have such a table, we can insert the data into such a table. And in the first query, the default TTL value will be used that we have created on the previous slide. We can also override this value by using TTL clause. And similarly, when we use update query, we can specify the TTL value also that way. When we query the data, we can use the TTL and write time functions to determine what's the TTL of some particular column. So for example, you have a heart rate column, and this heart rate column has some different TTL values per each row. And we also see the write time, the time that the row was inserted, that this particular column was updated, inserted. And by combining those two parameters, Scylla knows now when this particular column, this particular value should be expired. And actually, if you wait long enough and you execute the same query, now this query will not return any new rows, and this query will expire those previous queries. So now maybe it's a section when I show different techniques that you can reimagine the already existing tables and query them in different ways. So let's start with materialized views, and to better explain this feature, I'm going to create an example table that has some partition key and some clustering key. And as you know, when we specify a partition key, this allows us to efficiently query all the rows that have some specific partition key. And additionally, the clustering key allows us to define different ranges. So we can, for example, select some values, some rows that have some particular pet chip ID and are from some specific period of time. So this is how a select might look from that table, and the dark blue column is the partition key, and the cyan column is the clustering key.
Piotr, we have two questions here on the chat. The first one is, how would you update the time to live for old entries in the database? You can go for this one first, and then we go to the another.
Yes, so there isn't any shortcut that you could do. So essentially, this means that you have to do some scan of the table and know all the partition keys, all the cluster keys that are stored in the table. So do a select scan of the entire table and execute some update statements that update all the TTLs. So unfortunately, in that case, you have to do a full scan and full update of the table.
While updating a column in the table, how can we make sure that TTL value for that column remains the same as for the other columns?
Okay, so in the case that you have, if you don't specify the TTL in queries directly and you just rely on the default TTL value, then updating the column value, of course, it will change the write time, but it will update the TTL value because you are always inserting with the same TTL value. So I think answering this question, if you have some queries that all use some different TTL values, then and if you don't want to update the write time, then you have to use the update with some different timestamp to specify a new write time that might be more closer to the original write time in the table.
Okay, thanks for the answer.
Okay, so going back to the example, so we have a table that has some petchip ID partition key and time, which is clustering key. And that's all great. We can select all the data that has some particular petchip ID. However, there's a problem because if you want to select a data, some rows from this table that have some particular owner, then Scylla won't allow you to do such a query. Scylla will tell you that doing this query will have Scylla scan over all the table, all the data in the table, which can be a quite expensive operation with unpredictable performance. Of course, you can override this behavior and specify that you allow filtering, but Scylla will then query and scan through all the rows in the table. This is where materialized view come in, and in the slide we create a materialized view that presents the table in a different view, in a different way. So in the original table, the petchip ID was the partition key, but in the materialized view, now the owner is the partition key, and this allows us to query all the data that has a particular owner value. So this is how the data is transformed. So we still have the base table, but now we have another table, the view table, the materialized view table, which has a different partition key. When we do an insert, what happens under the hood is that Scylla sends the request to the base table, and automatically, without you having to do anything, this insert is also persisted in the materialized view table. So materialized view are very, very powerful tool in your tool chain. However, in most cases, using secondary indexes, either local or global indexes, can be a better choice. So in this slide, we try to achieve a similar thing that we did on the previous slide. So we still have the same table that has the petchip ID as a partition key, but we want to do some queries that query the data from particular owner. And creating an index is a great way to allow such a query to execute very quickly. And using a create index statement allows us to do and create such an index.
Okay, can we update via the view?
Uh, yes, so you can't do any updates through the view, only do the selects through the view.
I guess that is the update.
Yes. So when you create an index and insert the data into the global secondary index, a very similar thing happens as in the case of the materialized view. So the data is inserted into the base table, and all this insert is then replicated in the index structure. When you do a query, then the query first looks on the index table and reads from the index and persists the data, reads from the index, and then you can use this persisted index table to efficiently select from the base table. So there are also another type of indexes. So there are local indexes, and those local indexes get around the problem that was shown in the previous slide. So as you can see, when we do a query to a table that has a global secondary index, we could need to query two different replicas. So we would need to query two different nodes. What local indexes allows us to do is to get around this issue, and the way that it achieves is that the local secondary index has to be partitioned on the same partition key as the base table. So in this example, we create an index also on the owner column. However, we have to specify that the index is also on the pet chip ID, which is the original partition key. This will mean that our queries will be less flexible. So we will have to query on both the pet chip ID restriction and the owner restriction. But the advantage of it is that when we insert to such a table, the base table and the index for some particular row will be on the same node. And all the data that we query in selects will be also queried only from a single replica set. One new feature that was added in recent versions of Scylla allows us to do also indexes on collections. And this is a very powerful feature that I think will allow for much more flexible data models in Scylla. So when we have a table that has some collection types, such as maps, lists, sets, we can do indexes on values from those collections. And that allows us to do queries on the table that select all the rows that have a collection that, for example, contains some particular value. So if we have some list with some, for example, some scores, we can select all the rows that have some collections that have a particular score in that list. And this is all done using the index machinery that we have in Scylla. So this will have a good performance when you do the queries. So now maybe going into the finishing stage of the presentation, we'll talk about using Scylla monitoring and using it to troubleshoot Scylla and to get to know how the cluster is working, what are the number of requests that are happening on the cluster. So this is the main dashboard of Scylla monitoring, and this has all the main information that you want to have about the Scylla cluster, what's the load on the cluster, the CPU load, how many writes and reads are happening on the cluster, and the latencies of writes and reads, and if you have any timeouts that could mean that the cluster is overloaded. Apart from this view, there's also a handy button that allows you to jump into different views, and those views can be very advanced and specify different parameters of different components of Scylla. So you can very quickly see which one has the greatest impact on the performance of the cluster, and also see how much disk is used and other very important metrics. So now the most interesting part of the demo, of the presentation, I think we'll go through a demo presenting those different features of Scylla. And actually, we are going to use Scylla Cloud as a handy way to create a cluster and have a ready-made dashboard, Scylla monitoring dashboard, to get to know the state of the cluster.
We have 10 minutes left, so I'm going to wait until you finish your presentation, then come with questions from the chat, okay?
Okay, so I think 10 minutes will be necessary for all the demos that I've presented. So maybe showing the cluster. Here's Scylla Cloud, and I have created a small cluster, Scylla University cluster. It's very easy to connect to this cluster. On the Connect tab, you have many instructions for different languages, and you can copy paste the code and very quickly connect to the cluster. So let's start with the first topic that I mentioned, which is using Shard-aware drivers. And here I have written some example program which connects to the Scylla cluster, Scylla Cloud cluster. It will execute some statements that query some row from the table. And we execute the statements, and we also gather the execution information. So we have enabled the tracing of the statement. And by doing that, we know all that happened in Scylla when processing this query. So I gather the information of all the shards that have processed this query. So when we run this example, and at this moment I'm using a non-shard-aware driver, as you can see, some queries only contacted a single shard, but some queries had to go through multiple shards to get the result of the data. And the problem with that is that we are using the non-shard-aware driver, which doesn't know that this particular query had to contact shard 0 directly. Thankfully, it's very easy to change the non-shard-aware driver to a shard-aware driver. We maintain forks of different drivers that have shard-aware capability. So it's as simple as changing the dependency to use our own dependency. We can update the Maven project. And we can rerun the example once again. And while we wait for the example to run, first of all, you see this message, the using optimized driver. And by viewing that, you see that the driver is really the shard-aware driver. The second thing that you can very easily see is that the queries that we have performed are now only processed by a single shard. So there isn't any need to contact multiple shards and have the shards transfer the data between themselves. So this will have a much better performance. And also another thing to point out is that I only changed the dependency, but we didn't have to update the code in any shape or form. So our forks are compatible with our existing code, so it's a really clean and fast drop-in replacement. The next example that I'm going to show is regarding the prepared statements functionality. So we have a very basic example that is going to perform some selects from the table. And at this moment, we do something really bad. So we create the statement and we just concatenate different parts of the statements on our own. Of course, when we run the example, this will work correctly. So it will select the data from this table, as we will see in just a second. Yes, so the row was selected. However, this also can cause some security issues because if PK was some string, the attacker could inject some part of query in that point and execute some other query. So to get around it, we'll not join the query on our own. Instead, we'll insert the bind marker. in those two places. And it's very easy to pass this parameter to the bind markers. So we just specify the two parameters at the end of the execution. And that way the statement can now use those bind markers. However, there's still a problem because we are still using an unprepared query. So to prepare the query, we can use the session prepare method, passing the same query. And then when we use session execute, instead of passing the query string, we pass the object, the prepared statement object, but we have to bind the values, the actual values to this statement. So we bind the pk, ck values, and this will work and function the same way as the previous two ways of executing this query. While we are at this example, maybe showing some other features, specifying the retry policy is as simple as using the with retry policy method on the cluster builder part of the program. We can, for example, specify a fall-through policy, and this policy will just immediately throw an exception and do not retry any queries once again. So this concludes the Java driver part of the presentation. Let's very quickly move to the SQL-SH prompt. And let's quickly see how indexes can be created. So let's create a table. Let's insert some data into the table. And without using an index, we wouldn't be able to execute such a query. For example, selecting all the rows that have v1 equal to 3. Scylla will complain that doing this will have the Scylla cluster scanning the entire table. But as simply as creating an index on this column, this will be the global index. This will allow us to do this query very efficiently. So now maybe moving to the Scylla monitoring part. So when you use Scylla Cloud, going to Scylla monitoring is very easy. You can just click the monitoring button, and within a few seconds.
About monitoring itself,
Yes.
there is any retry related metrics available?
So when the retries are done from the client side, there aren't any metrics in the Scylla monitoring part. When some retries would be done internally in Scylla, I can't think of the specific name, but I believe that there would be some metrics regarding that.
Well, 1 minute left.
Okay, so maybe very quickly looking at the dashboard, maybe in the background, I will run some Cassandra stress that is going to perform some operations on this cluster. And within a few seconds, we'll see that the number of writes has increased. So this is the main view of Grafana. You can specify different periods of time. So maybe only showing the last 5 minutes that have what was the state of the cluster in the last 5 minutes. You can specify different updates. So maybe you want to have this dashboard updated every 5 seconds. So when this dashboard updates, we can see that the number of writes has increased. This is the background load that I have just started. When you try to debug some issue on Scylla monitoring, it's always great to look into advanced and detailed tables. So let's move on to the advanced view. And in this view, you can see the different bandwidths, the actual disk, how much it is used. And you can see that comic log is using 2 megabytes per second. The compaction process is using almost 15 megabytes per second. And when you debug some real issues with the cluster, it's always great to not only see the view by DC, so not viewing the different metrics overall, but also switching to a per shard view. So that way you can see how each shard is performing and whether there's some imbalance in some shard. Of course, there's lots of more to talk about in Scylla monitoring. I believe that Amnon has presented very many presentations about Scylla monitoring. So if you want to learn more about Scylla monitoring, make sure to also see the presentation by Amnon about Scylla monitoring. So I think that concludes the presentation, and we can move on to the Q&A.
Okay, thank you so much, Piotr. Right now, probably Sa, and let me check. Guide Sa is going to be answering question on the stage called expert panel discussion. And see you guys there. Thank you so much, everyone. And bye-bye.
Thank you.
Piotr.
Bye.